Welcome! In this session, we'll explore problem number 1123, lowest common ancestor of deepest leaves. This problem involves finding the common ancestor of the deepest nodes in a binary tree, a popular question in coding interviews. Let's dive in and break it down step by step. In this problem, you're given the root of a binary tree, and your task is to find the lowest common ancestor, or LCA, of the tree's deepest leaves. The deepest leaves are the nodes that exist at the maximum depth of the tree. The lowest common ancestor of a group of nodes is the deepest node in the tree that has all the nodes as its descendants. Importantly, a node can also be considered a descendant of itself. The input to this problem is a binary tree represented by its root node. Each node has a value, along with references to its left and right child nodes, which could be null if a particular child does not exist. The output should be the LCA node, returned as a tree node object. To better understand the problem, let's look at an example. Here, the input is a binary tree where the root node is 3, and it has two children, nodes 5 and 1. Node 5 further branches out to node 6 and 2, while node 1 has a single child, node 0. Among these nodes, the deepest leaves are nodes 6, 7, and 4, all located at depth 3. The lowest common ancestor of these deepest leaves is node 2, because it is the deepest node that has all three of them as descendants. So, the output for this example is node 2. Now, consider another example. In this tree, the root node is 1, and it has two children, nodes 2 and 3. The deepest leaves here are nodes 2 and 3, both at depth 1. The lowest common ancestor of these two nodes is the root node itself, since it is the only node that has both 2 and 3 as descendants. Therefore, the output is node 1. For a simpler case, imagine a tree with just one node, like node 1. Since it is the only node in the tree, it is also the deepest leaf, and naturally, the lowest common ancestor is the node itself. So, the output is 1. The constraints of the problem indicate that the number of nodes in the tree can range from 1 to 10,000, and every node in the tree will have a unique value. Additionally, the input will always represent a valid binary tree. When considering edge cases, there are a few specific scenarios to think about. For instance, in a single node tree, the single node itself is the LCA. In a perfect binary tree, where all leaves are at the same depth, the root will always be the LCA. In a skew tree, where all nodes lie on one side forming a single path, the deepest leaf is the last node, and the LCA is the leaf itself. Finally, for larger inputs, where the tree has up to 10,000 nodes, it's crucial to ensure that the solution is both time and space efficient. The algorithm should be capable of handling such inputs within the given constraints without exceeding memory limits or taking an unreasonably long time. Designing an optimal solution that accounts for these factors will be key to solving this problem effectively. To begin solving this problem, we initially consider the brute force approach, which involves separating the depth calculation and the LCA determination into multiple steps. First, we traverse the tree to calculate the maximum depth, which tells us how deep the tree goes. Once we know the maximum depth, we perform another traversal to collect all nodes at this deepest level. Finally, we compute the lowest common ancestor of these deepest nodes, which may require additional tree traversals. While this approach is straightforward and easy to understand, it is inefficient because it involves redundant traversals, particularly during the repeated LCA calculations. This inefficiency makes it impractical for larger trees, as the time complexity can grow to n squared, in the worst case, where n is the number of nodes in the tree. A more efficient solution is the optimized approach, which combines depth calculation and LCA determination into a single traversal using post-ordered DFS. The key idea here is to traverse the tree recursively in a bottom-up manner, calculating both the depth of each node and the LCA of the deepest nodes within its subtree simultaneously. In this approach, a helper function returns two pieces of information for each node, the depth of the subtree rooted at that node, and the LCA of the deepest nodes in that subtree. By comparing the depths of the left and right subtrees during the traversal, we can decide the LCA at each step. If the depths are the same, the current node becomes the LCA. If one side is deeper, the LCA is propagated from the deeper subtree. This method is highly efficient, with a time complexity of n, since each node is visited only once, and a space complexity of h, where h is the height of the tree. Its elegance lies in avoiding redundant computations, making it an ideal solution for this problem. Another possible method is the top-down depth tracking approach. Here, we traverse the tree while maintaining depth information for each node. As we traverse, we identify the deepest nodes and track them. Once we've collected all nodes at the deepest level, we perform a final computation to determine their lowest common ancestor. While this approach is also time efficient, with a complexity of O(n), it requires additional bookkeeping to track depths and deepest nodes, making it more cumbersome than the postorder DFS method. This extra overhead, combined with the need for multiple traversal phases, makes it less appealing. For these reasons, we favor the optimized approach over this alternative, as it is more streamlined and avoids unnecessary complexity. The key insight for solving this problem lies in realizing that the LCA of the deepest nodes will always lie at the intersection of the deepest paths in the tree. This observation allows us to leverage the properties of postorder traversal to determine both the depths and the LCA in a single pass. By comparing the depths of the left and right subtrees during the traversal, we can directly identify the LCA without requiring additional steps. When comparing the three approaches, the brute force method is the least efficient due to multiple redundant traversals. The top-down approach, while better, still involves extra bookkeeping that complicates the implementation. In contrast, the optimized postorder DFS approach is both simple and efficient, with a time complexity of O(n) and a space complexity of O(h). It is the clear choice for this problem, offering a clean and effective solution by solving both depth calculation and LCA determination in one seamless traversal. To solve the problem of finding the lowest common ancestor of the deepest leaves in a binary tree, we start by breaking it down into clear steps. First, let's understand the concept of the lowest common ancestor, or LCA. This is the deepest node in the tree that serves as an ancestor to all of the given nodes. If the tree has multiple deepest nodes, the LCA must encompass all of them. The initial step in the algorithm is to traverse the tree to determine the maximum depth. This can be done using a depth-first search, or DFS, starting from the root. During this traversal, we calculate the depth of each node and keep track of the maximum depth encountered. The key operation here is maintaining a max_depth variable, which ensures we capture the greatest depth in the tree. This works because a full traversal guarantees that we account for every node and its depth. Next, we focus on identifying all nodes at this maximum depth. For this, we can perform another DFS, or enhance our first DFS with an additional check, to collect these nodes. We store them in a data structure, such as a list called deepest_nodes, which holds all nodes whose depth matches max_depth. This approach ensures that we accurately pinpoint the target nodes for which we will compute the LCA. Now that we have identified the deepest nodes, the next step is to compute their lowest common ancestor. This involves performing a recursive LCA calculation starting from the root of the tree. For each node we visit, we check if it is one of the deepest nodes. If it is, we immediately return the node. Otherwise, we recursively search for the LCA in both the left and right subtrees. Here's the key decision: if both the left and right subtrees return non-null values, it means the current node is the lowest common ancestor because it is the point where the two branches converge. This works because we ensure that the LCA is the lowest node that covers all the target nodes. The algorithm is efficient due to its DFS approach, which visits each node exactly once. By separating the steps of finding the maximum depth, identifying the deepest nodes, and then computing the LCA, we achieve a modular and clear structure. Additionally, the recursive divide-and-conquer approach to finding the LCA aligns perfectly with the hierarchical nature of trees, making the solution both intuitive and effective. To implement this algorithm, we rely on a few key data structures. A stack is used for the DFS traversal, which can be done either iteratively or recursively. To store the nodes at the maximum depth, we use a list called deepest_nodes for easy lookup during the LCA computation. Finally, variables such as max_depth help track the deepest level reached during the traversal. When considering edge cases, the algorithm handles all scenarios robustly. In a single node tree, the root itself is both the deepest node and the LCA. If all nodes in the tree are at the same depth, the LCA is the root since it covers the entire tree. For unbalanced trees, the algorithm effectively identifies only the nodes at the maximum depth, regardless of the tree's structure. In terms of complexity, the algorithm is highly efficient. The time complexity is O(n), where n is the number of nodes, as we perform a DFS to calculate depths, another DFS to find the deepest nodes, and a final traversal for the LCA computation. The space complexity is O(h), where h is the height of the tree, due to the recursion stack used during DFS. This makes the solution scalable and well-suited for binary trees of varying sizes and shapes. This solution efficiently calculates the lowest common ancestor, LCA, of the deepest leaves in a binary tree using a depth-first search, DFS, approach. The LCA deepest leaves function defines a helper function DFS that returns two values for any given node, the depth of the deepest leaf below it and the potential LCA at that depth. The base case checks if the node is none. If so, it simply returns a depth of 0 and none is the LCA since an empty subtree has no nodes. For non-empty nodes, the function recursively explores the left and right children, calculating their respective depths and LCAs. After obtaining the results from the left and right subtrees, the function compares their depths. If the left subtree is deeper, the current node's LCA is inherited from the left subtree. Similarly, if the right subtree is deeper, the LCA is inherited from the right subtree. If both depths are equal, the current node becomes the LCA since it is the ancestor of leaves at the same maximum depth on both sides. The results of the recursive calls are combined by incrementing the depth by 1, accounting for the current node, and determining the appropriate LCA. Finally, the function returns the LCA stored in the result of the DFS traversal starting from the root. This approach ensures that the time complexity is O(n), where n is the number of nodes in the tree, because each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we start with the LCA deepest leaves method, which takes the root of the tree as input and returns the lowest common ancestor of the deepest leaves. The core logic lies in the DFS helper method, which performs a depth-first search on the tree. Within the DFS method, we handle the base case first. When the input node is null, we simply return a new result object with a depth of 0 and a null LCA. Next, we recursively call DFS on the left and right children of the current node to compute their respective results. Once we have the results for both subtrees, we compare their depths. If the left depth is greater, we return a new result that includes the left depth increment by 1 and retains the left LCA. Similarly, if the right depth is greater, the result is based on the right subtree. Otherwise, if both depths are equal, it means the current node is the lowest common ancestor for the deepest leaves at this level. In that case, we return a result with an increment depth and the current node as the LCA. To support this logic, we define a static inner class called result. This class has two fields, depth, which tracks the depth of the subtree, and LCA, which holds the lowest common ancestor of the deepest leaves within that subtree. The constructor initializes these fields with the provided values. Additionally, we define a treenode class to represent the nodes of the binary tree. Each node has an integer value, as well as left and right child references. By combining these components, our implementation efficiently computes the LCA of the deepest leaves using recursion and depth comparison, ensuring clarity and modularity in the code structure. To solve the problem of finding the lowest common ancestor of the deepest leaves, we start by considering a balanced binary tree. Here's the given tree structure. The process begins by performing a depth-first search, or DFS, starting at the root node, which is 3. From node 3, we first explore its left child, node 5. At node 5, we further explore its left child, node 6. Since node 6 has no children, both its left and right subtrees return a depth of 0 and no associated node. Since the depths are equal, the current node, 6, is considered the lowest common ancestor at this level, and we return a depth of 1 along with node 6. Next, we move to the right child of node 5, which is node 2. At node 2, we begin by exploring its left child, node 7. Node 7 has no children, so both its left and right subtrees return a depth of 0 and no associated node. This means node 7 is the lowest common ancestor at this level, and we return a depth of 1 along with node 7. Next, we explore the right child of node 2, which is node 4. Similarly, since node 4 has no children, both its left and right subtrees return a depth of 0 and no associated node. Node 4, therefore, becomes the lowest common ancestor at this level, and we return a depth of 1 along with node 4. Now, comparing the depths of nodes 7 and 4, we find they are equal, so the current node, 2, becomes the lowest common ancestor at this level with a depth of 2. Returning to node 5, we compare the depths of its left subtree, which is 1 from node 6, and its right subtree, which is 2 from node 2. Since the right depth is greater, we return a depth of 3 along with node 2. Now we move to the right child of the root node, which is node 1. At node 1, we first explore its left child, which is null, so we return a depth of 0 and no associated node. Next, we explore its right child, node 8. Since node 8 has no children, both its left and right subtrees return a depth of 0 and no associated node. This makes node 8 the lowest common ancestor at this level, and we return a depth of 1 along with node 8. Comparing the depths of node 1's left and right subtrees, we find the right depth, 1, is greater than the left depth, 0. So, we return a depth of 2 along with node 8. Returning to the root node, 3, we now compare the depths of its left subtree, which is 3 with node 2 as the LCA, and its right subtree, which is 2 with node 8 as the LCA. Since the left depth is greater, the lowest common ancestor of the deepest leaves in this tree is node 2, with a depth of 4. In the next example, we consider a simpler tree with only a single root node, 1. Since there are no other nodes, the root itself is the lowest common ancestor of the deepest leaves. For the right-skewed tree, the process begins at the root node, 1. First, we explore its left child, which is null, so we return a depth of 0 and no associated node. Next, we move to the right child, node 2. At node 2, we again explore its left child, which is null, and return a depth of 0 and no associated node. Then, we proceed to its right child, node 3. Since node 3 has no children, both its left and right subtrees return a depth of 0 and no associated node. This makes node 3 the lowest common ancestor at this level, and we return a depth of 1 along with node 3. Comparing the depths at node 2, the right subtree has a depth of 1 from node 3, which is greater than the left depth of 0. Therefore, we return a depth of 2 along with node 3. Finally, at the root node, 1, we compare the left subtree depth of 0 with the right subtree depth of 2 from node 3. Since the right depth is greater, the lowest common ancestor of the deepest leaves in this tree is node 3, with a depth of 3. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. This is because the DFS function visits each node precisely once during the depth-first traversal. For every node, only a constant amount of work is performed, such as retrieving the depths and LCAs of its left and right subtrees, making a comparison to determine which subtree is deeper or if their depths are equal, and calculating the depth of the current node as the maximum of the left and right depths plus 1. Since each of these operations takes O(1) time and there are n nodes in total, the overall traversal results in O(n) time complexity. This holds true across all scenarios, whether the tree is balanced, skewed, or irregular, as every node must still be visited once. The space complexity of the solution is O(h), where h is the height of the binary tree. The main contributor here is the recursion stack used during the depth-first traversal. In the worst-case scenario, such as a completely skewed binary tree, the height of the tree equals the number of nodes, or n, which leads to a space complexity of O(n). In the best-case scenario, like a perfectly balanced binary tree, the height of the tree is logarithmic with respect to the number of nodes, or log n, resulting in a space complexity of O log n. Importantly, the algorithm does not use any additional heap memory since it only stores local variables, such as depths and LCAs, within each recursive call. Therefore, the space complexity depends entirely on the recursion stack and aligns with the height of the tree, whether in the best, worst, or average case. To better understand the efficiency of this solution, let's compare it to a naive or brute force approach. A naive method might involve multiple traversals of the tree, first to calculate the depth of all nodes, then to identify the deepest leaves, and finally to determine their lowest common ancestor. This repetitive traversal could lead to a time complexity of O(n squared, in the worst case, as seen in a skewed binary tree where large subtrees are repeatedly processed. In contrast, the current approach integrates all these steps into a single traversal. By calculating depths, identifying the deepest leaves, and determining the LCA simultaneously, the time complexity is reduced to O(n). Additionally, the space complexity of O(h) is optimal for a recursive solution, as it uses only the recursion stack without requiring any extra memory, making this solution significantly more efficient than the brute force alternative. In summary, the solution achieves a time complexity of O(n), as each node is visited exactly once, and a space complexity of O(h), which corresponds to the height of the binary tree. This makes the solution both time and space optimal for the problem. Compared to brute force approaches with higher time complexity, such as O(n²), in the worst case, the current method is far more efficient. By combining depth calculation, deepest leaf identification, and LCA determination into a single traversal, the solution minimizes redundant work and ensures optimal performance for trees of all shapes and sizes. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases can lead to significant errors. For example, if the tree is empty or has just a single node, you might encounter null pointer exceptions or incorrect results. To avoid this, always check these base cases explicitly. For an empty tree, return null, and if there's only one node, simply return the root. Another frequent issue is inefficient depth calculation. If you perform multiple traversals for depth computation and identifying nodes, you're introducing unnecessary redundancy. Instead, optimize your solution by combining these tasks into a single traversal. Lastly, be cautious with your LCA logic. It's easy to mistakenly assume that the lowest common ancestor of the deepest leaves must always be at the deepest level. However, the LCA might be higher up in the tree if the deepest nodes are spread across different subtrees. To address this, ensure your recursive solution considers both left and right subtrees properly. Another potential pitfall is mutating shared state during recursion. Using global or shared variables without proper management can lead to subtle bugs, especially if the state isn't reset before each function call. Instead, rely on return values to pass information up the recursion stack. This approach is cleaner and less error-prone. Additionally, some solutions overlook the possibility of unbalanced trees. Assuming the tree is balanced can lead to failure in certain edge cases or suboptimal solutions. Always ensure your approach can handle unbalanced trees effectively. From an interview perspective, it's important to recognize patterns in tree problems. Many of these challenges are best approached using recursive divide-and-conquer strategies, so mastering tree traversal techniques like depth-first search and post-order traversal is crucial. Interviewers also value solutions that minimize redundant work, so strive to combine tasks like depth calculation and LCA identification into a single traversal. Finally, while recursion is often the intuitive choice, be prepared to discuss iterative alternatives as they may be necessary for handling large trees where recursion could cause stack overflow. To deepen your understanding, it's helpful to explore related problems. For instance, problem 1123, the lowest common ancestor of deepest leaves, is closely tied to problem 236, the lowest common ancestor of a binary tree, and problem 865, the smallest subtree with all the deepest nodes. These problems share similar concepts but may differ in their constraints or focus. Another related problem is problem 543, the diameter of a binary tree, which also involves tree traversal and recursive strategies. In terms of alternative approaches, one efficient method is performing a single traversal using recursion. This combines depth computation and LCA identification into one DFS traversal, achieving optimal time complexity. However, while this method is efficient, it can be harder to debug if you don't carefully manage the recursion stack. Another option is using BFS with level tracking. This involves level order traversal to identify the deepest nodes, followed by a separate step to compute the LCA. Although this method is easier to implement, it requires additional space to track the nodes at each level. Finally, the divide-and-conquer approach is another powerful alternative. By leveraging post-order traversal, you can compute both the depth and the LCA of the deepest nodes in a single recursive pass. This method is elegant and highly efficient, making it a great choice for this type of problem. However, it does require a solid understanding of recursive tree traversal patterns. If you're comfortable with recursion, this approach can simplify the problem and help you directly address both tasks, depth calculation and LCA identification, without redundant computations. With practice, mastering these strategies will make you well prepared to tackle variations of this problem and similar tree-based challenges. Great job! We've covered how to solve problem number 1123 using efficient traversal techniques. Remember to practice similar problems to build confidence in tree-based algorithms. Don't forget to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!